welcome to series lecture 19. This is going to be the last test that we have for convergence of infinite series, the root test. Next lecture is just going to be some samples of using these tests. The root test is sort of specific. It's useful in a certain type of series, in particular those that are where the terms are raised to the nth power. But it's another test, just like the ratio test, that tests for absolute convergence versus divergence. And I forgot to give you a quick reasoning on the ratio test of why it works, even though it's not a formal proof. Let's just quickly look at what the ratio test was saying again. It was looking at the limit as n goes to infinity of a to the n plus 1 over a to the n, right? And it said if this limit is less than 1, then it converges. If it's bigger than 1, if it's less than 1, it converges absolutely, not just converges, but it converges absolutely. If it's bigger than 1, it diverges. It doesn't even converge conditionally. It just converges. It just diverges point blank. There's no convergence at all there. If it's equal to 1, it may converge absolutely. It may diverge. It may converge conditionally. We can't tell what's happening there. But why does that work? I mean, the intuitive way of thinking about this, even though we're not proving it formally, is that, again, convergence is going to tell you, it's going to be dependent on how quickly your terms go to 0 for the most part. And if an plus 1 over an goes to 0 pretty quickly, that means if that ratio is getting smaller and smaller, that means that terms are going to 0 pretty quickly. The an plus 1 is bigger than the an, which sort of should hint that it might be more likely for it to converge. Not formally, but it should be a good hint of it. And if the an plus 1 over an is going to something bigger than 1, that means an plus 1 is not getting small quick enough to counter the an. So I mean, the intuitive thinking about this is if that limit is small, then the terms are going to 0 fast enough for it to converge absolutely. Now, if that limit's equal to 1, so all those alternating series that converge conditionally, but not absolutely, like the alternating harmonic series, if you try the ratio test on that, you're going to get a limit of 1. So it's not converging. So the ratio test simply doesn't work. But the root test is a similar type of test. It really is, and it works for a similar reason, although we're not going to give a formal definition, a formal proof of this one either. But in the root test, we're looking for the nth root of the absolute value of the nth term. So rather than taking the ratio of the n plus first term to the nth term, we're taking the nth root of the nth term, or the absolute value of that. And the idea is that if that, you are taking the limit as n goes to infinity of that, if that limit's equal to L, which is less than 1, then the series converges absolutely. And if it's equal to some limit that's bigger than 1, it diverges. It doesn't even converge conditionally, it diverges. And if the limit's equal to 1, then we can't draw any conclusions. It may converge, it may diverge, it may converge absolutely or conditionally. Again, intuitively, to think about this, if that limit's less than 1, that means these ANs are getting small pretty quickly. Okay, if the limit's bigger than 1, the ANs aren't getting small quick enough to converge. So that's really what's happening. These are both tests to tell you how quickly these ANs are getting small. So let's go down to this example. This is a classic example of where we would use the root test because the terms are raised to the nth power. So this is all positive, so we don't have to, as long as n is bigger than or equal to 1. So we don't have to worry about absolute values. So we're just going to look, if it converges at all, it converges absolutely. So I'm going to look at the limit n goes to infinity of the nth root of this term. And of course, what's nice is the nth root gets rid of that exponent, and we get the limit as n goes to infinity of 3n plus 4 over 2n plus 1, which is 3 halves. which is bigger than 1, so this thing diverges. So that diverges. I think you could probably also show those terms don't go to 0 as well. But your idea is the classic use for the ratio test, for the root test, is if your terms have a power of n as part of that term. Okay, and I think this is probably a good place to stop. Short lecture indeed, but there's not much to say about the root test.